All right, so the method of undetermined coefficients, what we talked about last time, it is a powerful method for solving non-homogeneous differential equations, but we have some limitations. Our coefficients have to be constant, and our function, the g of x, the right-hand side of the differential equation, has to be of a particular form. So those are kind of limiting factors to variation of parameters. So the method we're going to use today can be used. Our coefficients don't have to be constant, and our g of x doesn't have to be any particular type of function. But I want to look at the solution to a first-order linear differential equation for some motivation for the method. So if we go back to y prime plus p of x y equals f of x. And we solve this one by finding our integrating factor, turning the left-hand side into the derivative of product, etc. We can write the solution as, if you like formulas, you can write your solution like this. Y equals C1 e to the negative integral of p of x dx plus e to the negative integral p of x dx times the integral of e to the integral of p of x dx f of x dx. You remember we ended up dividing both sides by e to the p of x dx at the very end when we had our product here on the left-hand side. So we can, I think this is essentially the formula that you showed me the other day. Yeah. So we can think of the solution like this. Well, this looks like y equals y sub c plus y sub p, our complementary solution plus our particular solution, where y sub c is c1 e to the integral negative p of x dx, and y sub p is this big thing, e to the negative integral p of x dx integral e to the integral p of x dx f of x dx. And we would see if we set this equation equal to 0, y prime plus p of x y equals 0, the solution to that equation, that is a separable equation, and this is the solution to that homogeneous equation. So we can think of this as the complementary solution plus a particular solution for the homogeneous, or the non-homogeneous equation. So let's look at a different method of thinking about this equation to find this solution. And that different method is the method that we'll use for second-degree differential equations. So now we're going to suppose y1 is a solution to y prime plus p of x y equals 0, the homogeneous equation. This is separable. So I'd write dy dx here, get all the x's on together, get all the y's together the way we usually do. And we would say, we would come to, when we solve that, we would get y1 equals e to the negative integral p of x dx is a solution. Now for this method, we want our particular solution, y sub p, to be some undetermined function, u1 of x times y1 of x. We want our particular solution to be this thing times, this thing times some other function. Because that's, when we go back here, that's what we ended up with. That thing times some other function. So we want this to be a solution. So that u1 of x is our variable parameter, if we want to think about it that way. Well, if this is a solution, that means that the derivative with respect to x of u1, y1 plus p of x u1, y1 equals f of x. If it's a solution, that has to be true. Well, if I take the derivative of this, I get u1 dy1 dx plus y1 du1 dx using the product rule plus p of x u1 y1 equals f of x. I'm going to gather all the terms with a u1 in them and factor that out. So u1 times dy1 dx plus p of x y1 plus y1 du1 of x dx equals f of x. Well, this term, or this portion in the parentheses, y1 is a solution to the differential equation, the homogeneous differential equation. So this equals 0. y1 is a solution to the homogeneous differential equation. So this entire term goes away, and we get y1 du1 dx equals f of x. And I can rewrite this as du1 equals f of x over y1 dx. And so our u1 is the integral of this. F of x over y1 dx. And y sub p is u1 y1. So that is going to equal y1 times the integral of f of x over y1 of x dx. And we know that y1 is e to the negative integral of p of x dx. And we get the same solution that we had before, by assuming that this particular solution to the non-homogeneous differential equation is this unknown variable parameter times our original solution. So this is the process we're going to use for a second order differential equation. We're going to assume that our new solution is some variable parameter times our solution to the homogeneous equation. All right. So does everyone understand our setup and our motivation? This gives us motivation for this, the motivation for this technique. For a second order differential equation, I'm going to say a sub 2 y double prime plus a sub 1 y prime plus a sub 0 y equals g of x. And here the a's, the coefficients, can be functions of x. Our first step, and this is important for this method, our first step is to divide by a sub 2 to get this in standard form. So we get y double prime plus, and I'm going to write p of x y prime plus q of x y equals f of x, where p of x is a1 over a sub 2, q of x is a0 over a sub 2, and f of x is g of x over a sub 2. So we want to start in standard form. And we know if p of x and q of x are constant, we can find y sub c equals c1 y1 of x plus c2 y2 of x because we know how to solve a homogeneous differential equation with constant coefficients. So if these two are constant, we can find y1 and y2. And that part is the kind of the weakness of this technique, is that we have to be able to find y1 and y2 to use variation of parameters. We have to be able to find those two solutions somehow. So right now, we're kind of limited to constant coefficients. All right, so now suppose that our particular solution to the non-homogeneous differential equation is u1 of x, y1 of x, plus u2 of x, y2 of x, where u1 and u2 are our variable parameters. We don't know them yet. So our goal is to find those. So this is why we call this method variation of parameters. These parameters are variable. Yes?
Do you include two parameters because it's a second?
Yes. All right, so now we're going to take some derivatives and plug them into our differential equation. So there's lots of superscripts, primes, and subscripts. So y sub p prime equals u1 y1 prime plus y1 u1 prime plus u2 y2 prime plus u2 prime y2. This should be y sub 2. And this should be y sub 2 prime. There we go. Y sub p double prime. u1 y1 double prime plus y1 prime u1 prime plus y1 u1 double prime plus u1 prime y1 prime plus u2 y2 double prime plus y2 prime u2 prime plus y2 u2 double prime plus u2 prime y2 prime. That's a lot of stuff. but it's just a second derivative. So y sub p double prime plus p of x, substituting into our equation, I'm just writing what our equation is now, p of x, y sub p prime plus q of x, y sub p. When we substitute all of this stuff in, I'm going to gather the terms that have a u1 and factor that u1 out. So we get u1 times y1 double prime plus p y prime, y1 prime, plus q y1. Factor the u2 terms out, the terms that contain u2, factor that out. Y2 double prime plus p y2 prime plus q y2. What do we know about these two? y1 and y2 are solutions to the homogeneous differential equation. So this term equals 0, and this term equals 0. So that's nice. But we have more. Plus y1, u1 double prime, plus u1 prime, y1 prime, plus y2, u2 double prime, plus u2 prime, y2 prime, plus p times y1 u1 prime plus y2 u2 prime plus one last term, y1 prime u1 prime plus y2 prime u2 prime. This term is the derivative of y1 u1 prime plus y2 u2 prime. That's why I gathered it all together. So these two terms are 0. So I can rewrite this as the derivative with respect to x. This term is y1 u1 prime plus y2 u2 prime. If I take the derivative of this with respect to x, I get this entire term.
Wait, like the derivative of y1 u, or like the derivative, or just y1 times u prime?
If I y1 times u prime.
Okay.
If I take the derivative of y1 times, u1 prime, y2 u2 prime, if I take the derivative of this, it expands out to this. Plus p times this thing, y1 u1 prime plus y2 u2 prime plus y1 prime u1 prime plus y2 prime u2 prime. That has to equal f of x. So we have two equations that we're solving for. So we're solving for u1 and u2. So it makes sense that we are going to need a system of equations. We're going to need two equations to solve for those things. So based on that, we're going to require make further requirements on u1 and u2. Require that this thing, y1 u1 prime plus y2 u2 prime equals 0. So we're going to put that requirement on those two functions. So that gives us one equation. Well, if these two terms then become 0, this is 0, this is 0, our second equation is this quantity, y1 prime u1 prime y2 prime u2 prime, has to equal f of x. Y1 prime U1 prime plus Y2 prime U2 prime equals f of x. There is our system of equations. Our variables are U1 and Y1. And our coefficients are Y1 and Y2, which are known. So then we solve this system of equations. U1 prime and U2 prime, and then we can integrate to find U1 and U2. So we're not going to go through and solve this system of equations by hand every time. We're going to take advantage of something from linear algebra called Cramer's rule. And by Cramer's rule is something that relates the determinant of the coefficient matrix to our solution. So if we go through the process of solving this system of equations by substitution, we would see that it comes out as these determinants of these matrices. So I'm just going to say by Cramer's rule, I don't think Cramer was French. We have U1 prime equals, I'm going to write it this way, W1 over W, which is also minus Y2 times f of x over W. And U2 prime is W2 over W, which is Y1 f of x over W, where W is the Wronskian that is the determinant of the coefficients. W1 is this Wronskian, but with the first column replaced by this right-hand side of the equation. So that's 0 f of x, y2 prime. And W2 is this determinant, but with the second column replaced by these two. So if you go through solving that system by substitution, and you write out just in function form what the solution is, this minus this multiplied by this, it turns out to be exactly this Wronskian, or this determinant divided by this determinant gives you the first variable, and this determinant divided by this determinant gives you the second variable.
How did someone figure this out?
Well, this isn't, I mean, if you write out, if you just wrote ax plus by equals some equals c, and dx plus ey equals some other f, and you wrote out the steps you did by substitution purely symbolically, you would see you get a determinant in the numerator and this determinant in the denominator. So that part is not difficult to see. The variation of parameters was figured out just like this. Yeah, we need a system of two equations. Let's substitute, see what we get, and see what requirements we have to have on those functions. Yes?
Why are we allowed to just say that y1 u prime plus y2 u prime equals 0?
Because it makes these go away, and it makes this equal to f of x to give us a... So we know that for a particular solution, all we need to find is any particular solution for the non-homogeneous equation. So that's all that's required, is to find any particular solution. So this allows us to find some particular solution.
So doesn't that mean we're in theory losing a particular solution?
I guess possibly. But we're not looking for everyone. All we care about is to find any particular solution.
Okay.
And we also know that because our Wronskian, it comes from our functions that are solutions of a homogeneous differential equation. The Wronskian is not 0 for all x, for every x in our interval, so we don't ever have to worry about dividing by 0. And we don't have to worry about our constants for our y1 and y2 because we're multiplying those things together, and the constants end up just being multiplied, and we just end up with a single constant. I always forget these, like which one is positive, which one's negative, but it's easy for me to remember, replace the first column by the right-hand side, replace the second column by the right-hand side. So I always write out the determinants, but if you prefer to remember a formula, I always get the minus sign and I forget which y1 and y2 go with this. So this gives us u1 and u2 prime, and then we can integrate to find u1 and u2. And then we multiply u1 by y1 to get our one particular solution, and we multiply u2 by y2 to get our second particular solution. And y sub p is y1, I'm going to say u1 y1 plus u2 y2. So to use variation of parameters, we need to find y1 and y2 by solving the homogeneous differential equation. And then we find u1 and u2 by forming these determinants and doing this, setting up this fraction and integrating. So let's look at an example. Y double prime minus 2y prime plus y equals e to the x over 1 plus x squared. So that is not a function there on the right-hand side that we could use undetermined coefficients to find. So we're going to use variation of parameters. So our homogeneous auxiliary equation is m squared minus 2m plus 1 equals 0. Well, that's m minus 1 squared equals 0. So we get a repeated root of m equals 1. So our complementary solution is c1 e to the x plus c2 x e to the x, since we have repeated roots. So y1 is e to the x, and y2 is x e to the x. Our Wronskian is e to the x, derivative of e to the x here, x e to the x, and the derivative of x e to the x here. The determinant of that. Well, when we do the Wronskian here, we get x e to the 2x plus e to the 2x minus x e to the 2x, which is just e to the 2x. So that's our Wronskian. W sub 1 is the determinant 0 e to the x over 1 plus x squared, x e to the x e to the x plus e to the x. So we always have the 0 here for our undetermined coefficient, so we just have one term to deal with. Here we get negative x e to the 2x over 1 plus x squared. And W2 e to the x, e to the x, first column of the Wronskian, 0, e to the x over 1 plus x squared. So this is going to give me e to the 2x over 1 plus x squared. So U1, I'm going to go over here. U1 prime is W1 over W. So this e to the 2x divides out this e to the 2x. So we get negative x over 1 plus x squared. U2 prime, we divide this by e to the 2x, and I just get 1 over 1 plus x squared. And we're going to integrate these two. Are we starting to do the integrals already in our heads? We know we get one of them an inverse tangent, right? This one's a nice u sub. I'm going to change pages now. So U1 is the integral of minus x over 1 plus x squared dx. That's a nice u sub. So that's just negative 1/2 natural log of 1 plus x squared. Negative because of this, the 1/2 because of this 2 here. U2 is the integral of 1 over 1 plus x squared dx, which is inverse tangent of x. And my particular solution then is minus 1/2 natural log 1 plus x squared plus inverse tangent of x. And the entire solution is y sub c plus y sub p.
Would you have a plus c or no?
No, because remember we don't need, for our particular solutions, we don't need their Fourier parameters. But the C1 and the C2 would come in our complementary solution.
Okay, yeah.
So when we add our complementary solution, which was this, we get our two constants. Yes?
Wait, for the particular solution, you do U1 times y?
Yeah.
Oh, did I forget to multiply? I forgot to multiply. Thank you. What's y1? E to the x. So I need an e to the x here. And I need an x e to the x in front of the inverse tangent x. There we go. Thank you. All right, let's look at one more. This one is fun, I think. Yes, but the simplification is more fun. Y double prime minus y equals sinh 2x. So our homogeneous auxiliary equation is m squared minus 1 equals 0. So m equals plus or minus 1. So our complementary solution is C1 e to the x plus C2 e to the minus x. This is a hyperbolic sine function. We have an e to the x plus e to the minus x. Keep that in the back of your head. So my Wronskian is, this is y1 and this is y2. So I get e to the x, e to the x, e to the minus x, minus e to the minus x. So the Wronskian is -1 minus 1, which is -2. So that's nice. W1, 0, sinh 2x, e to the minus x, minus e to the minus x. That Wronskian is -e to the minus x, sinh 2x. W2. Question?
Shouldn't that be positive?
It's this minus this.
Oh.
So that's where the negative comes from. W2, e to the x, e to the x, e to the, 0, sinh 2x. So this one comes out to be e to the x, sinh 2x. So u1 prime is this whole thing divided by -2. So u1 prime is, I'm going to write it as 1/2 e to the minus x sinh 2x, which is e to the 2x minus e to the minus 2x, so we can integrate over 2. And u2 prime is this divided by 2, so 1/2 e to the positive x, e to the 2x minus e to the minus 2x over 2, so we can integrate. So this comes out to be 1/4 e to the 3x e to the x, did them in the wrong order. E to the minus x times e to the 2x is e to the x minus e to the minus 3x. And this one comes out to be 1/4 e to the 3x minus e to the minus x. Wait, did I do that right?
We didn't make it on the calculation.
Oh, yeah, twice u is negative, or u prime 2.
That should be negative. That should be negative. Did I do something wrong here? Let me make sure. Okay. So now we're going to integrate. So u1 equals the integral, or I'm going to say 1/4, the integral of, what do we have? E to the x minus e to the minus 3x. Which equals, we get 1/4 e to the x minus 1/12 e to the minus 3x. And u2 is 1/4 negative 1/4 e to the 3x minus e to the minus x. Which is negative 1/4, negative 1/12 e to the 3x plus e to the minus x.
Should the top
Hang on,
one
this should be Hang on, am I doing my integral correctly?
1/4 should be 1/12.
Oh, I forgot my 1/3 here. I'm going to do it this way. E to 3x, 1/3, 1/4, like that.
On the top, I think you need a plus rather than in your answer. Pretty sure.
Yes, you're right.
I don't think this one was tough.
So we get, what do we get here? Minus 1/4 e to the minus x minus 1/12 e to the 3x for that one. So y sub p equals y sub 1 times e to the x plus e to the minus x times minus 1/4 e to the minus x minus 1/12 e to the 3x. And when I multiply this out, I get 1/4 e to the 2x plus 1/12 e to the minus 2x minus 1/4 e to the minus 2x minus 1/12 e to the 2x, which is 1/6 e to the 2x minus e to the minus 2x equals 1/3 sinh 2x. That was the fun part. And y equals y sub c plus y sub p. So based on this, could we have done this using undetermined coefficients? Yeah, because sinh is the sum of exponential functions. So we could have used undetermined coefficients to do this one as well. But wasn't this way more fun? All this nice algebra?
There's no chance I don't mess up a negative sign like this.
Yes, you can use variation of parameters on anything that you could use undetermined coefficients on. Yes.
Wait, so like way back when we were setting like y1 prime, y1 prime, whatever, to like f1, f max, and like the other one's 0. Is that just helping us like construct a mixture? Like making it easier so that we can plug in like 0 and f max into the w?
Well, if we make this requirement these equal to 0, these two terms go away, and then our equation tells us this has to equal f of x. So that gives us two equations then that we can solve for u1 prime and u2 prime. So making that requirement gives us, we need two equations and two variables to solve for those two because we have two unknowns. So this requirement gives us one of the equations, and that reduces the other equation. This equals f of x.
It's just convenient.
It's convenient. It makes it so that we can solve for the two unknown parameters and come up with a solution.
But this like in like w1 and w2 when we're like putting in 0 and f of x into like those, is that like
Yeah. So W1 is just the Wronskian matrix or determinant with the first column replaced by that right-hand side, and W2 is the Wronskian matrix with the second column replaced by that right-hand side. And when we solve this two-variable system by substitution, if we solved it symbolically, we would see that this comes out to be what our solutions are. So this Cramer's rule is something that comes out of linear algebra. All right. Questions? Yes.
Are we gonna have to do more than second order for this, or anything?
In this class we're only learning second order for variation of parameters.
And what would you do to make it if it was third order?
There's, there's a, well, I mean, the U1 prime and U2 prime are still just a Wronskian.
Okay.
Those Wronskians, and the W1 is the third column replaced by the right-hand side. So W2 is the middle column, W3 is, the first column, the middle column, so you'd have three of those. But you have a third condition that you have to impose on the function so that you get a third equation. If I remember right, I think there's another equation that you say, well, this equals 0 and this equals 0. So you get two of them that are zeros.
So there's like a Kramer law for like
You
for,
can
like undue order.
you can use Kramer's rule on any system of linear equations.
Yeah, you just
Oh, I made some amendments to this homework assignment, so let me grab the correct assignment.
It was about like average for me. No, I had 4 sheets of paper.
Yeah, it took me a front, a back, and a front.
Bro, this is like the Jacobian of
like yesterday.
That
Oh,
third
yesterday
term
I
is just so much more work. Maybe it'll use like the y sub p. It's all.
Yeah, when you have to start writing out, like, just symbolically, all those derivatives, it's just
And then there's like a subscript and
a subscript and a superscript, and it's just a lot of stuff.